We're going to continue today's lesson looking at Unit 11, the second half of which consists of dynamics. Now remember, dynamics is the study of forces, and also the idea of having kinematics or motion and forces as two disjoint topics is not really a good thing. They actually go together very well. In fact, very famous three laws are described here on this first slide. Newton's laws of motion. So we have three Newton's laws here, and these ones actually you can think of them as the bridge between dynamics or forces and kinematics or motion. We're not going to be analyzing Newton's laws in incredible detail. The main law that we're going to see a lot of in this course is number 3, which is for every action or every force, there is an equal and opposite reaction or force. When we say action and reaction, we're referring to a force. An example would be this. Let's say that you push on the wall. So imagine that you push on a wall. When you push on the wall, let's say that you're pushing, let's say the wall is south of you, so you're pushing to the south. Now, the reason that you don't go through the wall is because the wall pushes back at you. So if you push with a force of 100 pounds south, then the wall pushes back at you with a force of 100 pounds north. So that's an example of an action and a reaction. Forces in nature occur in pairs for that reason. And you might be wondering, well, wait a second. When I'm standing on the earth, gravity's pulling me down, but where's the opposite force? Where's the reaction to that? And the answer is you're pulling the earth up. Obviously, it's kind of interesting to see it like that, but it is the truth. You're pulling the earth as much as the earth is pulling you, because they're equal and opposite forces. So those are the types of forces, and gravity, of course, we'll consider in great detail. Those are the types of forces that you would see, for example, in construction, in statics, or the study of structures. The other Newton's laws here refer to how forces relate to an object that is moving. Now, we're not going to get into too much detail about Newton's first and second law because we're not going to be dealing with moving objects in terms of the analysis toward which we're heading. And that's because we're looking at statics, which is things that are not moving. So I do want to mention here that if all the forces balance on an object, Newton's first law says that the object, at most, will be going with a constant velocity. It could be at rest as well, because being at rest does mean that your velocity is constant with a value of 0. Newton's second law is a bit more interesting, and that's the one that most engineering students, for example, have burned into their brain by the first day of school, which is that F equals ma, or the net force that acts on an object is related to the acceleration and the mass. So that's Newton's second law right there. I've written it in a different way than most people would see in high school textbooks, because I'm just talking about the motion. I want to have motion on one side, and I want to have the force and the mass on the other side, the dynamics part, and the mass here, which is related to inertia. So anyway, let's take this formula for a little test drive and see how easy it is to use. And once we do a few examples of that, I'm going to talk a little bit more about the force of gravity. And then the rest of it is cruise control as we prepare for your test. And I just start looking at more questions involving forces and adding vectors together. So let's continue here on our path with examples 22, 23, and 24 to come. So we have here, what is the net force that would be required to accelerate a mass of 4.5 kilograms? Now this should be plural, but it's an adjective here, it's fine, at that rate of 2.56 meters per second squared. So the big equation here, remember, is Newton's second law, which is F equals ma. And in this case, that's the formula we'll be using. Now, force is a vectored quantity, as is acceleration. However, when we're talking about something as simple as this, we can assume that the direction is forward or whatever direction you will prefer. I'm not going to write directions for these. I'm just looking for the magnitude only. Because if you get confused about that, if I don't give you a direction in the question, just give us the magnitude for the answer. Like, don't worry about the direction. In this case, can someone do that calculation for us? So what's the mass here? Thank you, Sean. And the acceleration is 2.56 meters per second squared. I realize there's students in this audience that have taken physics before, so I hope you don't mind me going a little bit slow with this, because some people have never seen this before. Anyway, the units of force are newtons. So an important thing to take away from this example is that the units are kilograms for mass. Make sure you have kilograms here. I need to highlight this. You need to have kilograms, meters per second squared for the acceleration, and newtons for the force. Those go together, a package deal. If any of the units deviate from these most orthodox of the units for the metric system, it's important that you fix them to all look like that. So for example, if your mass is in I don't know, tons, metric tons that is, or the force is in kilo or thousands of newtons, or even if the acceleration is in centimeters per second squared or something like that, it's important that you recognize that the units are not the most orthodox of type, and you fix them. Newton's second law will only be done in the metric system in this course. The treatment in the imperial system is slightly different, and I'm not going to be doing imperial calculations since we're not dealing too much with physics of motion in this course. How did I get unit n? Joshua, they go together. It's a package deal. A Newton is the definition of the Newton comes from units of kilograms and meters per second squared. I'm going to close and reopen this file for a second. It's just glitching on me. Okay, good. It's working now. I'll just mention it here further to Joshua's comment. A Newton, 1 Newton of force is the force that is required. It's a good question, Joshua. That's why I'm actually just writing it here. Perhaps I could include that in my discussion earlier. But that's what a Newton of force is, okay? It's a definition as far as you're concerned for a unit. So the next couple of questions are simply permutations of this question. So in this case, we want the acceleration, and we're given the mass, and we're given the newtons. So take this formula, F equals ma, which is the famous Newton's second law, take that formula and shuffle it around and solve for A. So for this question, if you don't mind, and the next one that I do with you, I'm just going to screenshot my solution notes, because these are really easy questions, and there's no vectors involved, thank goodness. So it's nice to start off with a couple of questions here that are not vector. They are vector quantities, force and acceleration, but they're in a one-dimensional fashion, so we don't really write the direction here. I'm just using magnitudes. Plus, this question says magnitude anyway. So just take a moment to make sense of that one. You can see that the units are all nice. There's nothing weird. Let me know in the chat if you've never taken, who's never taken physics before but finds using this formula pretty easy. Okay. Anybody else? Good. You're my target audience. Awesome. It's a very famous formula. It's one that I can spend the entire unit on this one formula. People spend like weeks on this particular context or of the dynamics with Newton's second law. So question 24 is another permutation of this idea. Again, this time we're solving for mass. So if you don't mind, I'm just going to screenshot my answer and import it here. Keep in mind silly things that often get overlooked, like significant digits. Always fun times with those. So in this case, we're finding the mass. So it's useful to have the formula with its permutations. Now, if you're studying for the test, this type of question for Newton's second law is not in the textbook. So if I'm going to give you a question like this on your test, and most likely it's homemade. I'm going to just design the question myself and have it in my lab. But just for completeness here, F equals ma. Who's ever seen a triangle like this? Let me just, ooh, that's awful. Let me draw a nice big triangle. One of these formula triangles. Who's seen one of these before? Ever seen that before? A formula triangle? Oh, gotcha, Ravi. Yeah, so over here, for example, if you're solving for m, yeah, formula triangles. Now, for those that have studied, whoever studied electricity, I made a formula triangle. I call it a formula pyramid, but that's for another time. I don't do too much electricity teaching about electricity in this school at least. But there is actually one question in this book that comes from electricity and magnetism, which is going to be a little bit shocking to people while we're doing that. But it's basically just a vector question. Okay, I need to differentiate now the difference mass and weight. I need to differentiate those ideas. So let's go over here to the summary, page 2. And this is really, really, really important. Okay? So often, very often, people get these things wrong, okay? They get them confused. The difference between mass and weight. Mass and weight. So here's the bottom line, people. Weight is the force of gravity, okay? That's the force of gravity. That is the force that you feel because you're on a planet and it's pulling you down, or you're pulling it up. So weight is very specific with its units. In the metric system, weight is newtons. And in the imperial system, weight is pounds. Now, in contrast, mass is simply how much matter you have. It is the amount of matter that you have, or the amount of stuff that you have if you want. Mass is kilograms, but in the imperial system, mass is pounds. So you notice that in the imperial system, there is no distinction between mass and weight. They both have units of pounds. Often, you'll see that pounds will be written as lbf or pounds force, but the numerical value is the same. So as an example, let's say that it's me and I'm standing on the, or me or anybody. Let's say that it's someone standing somewhere on the earth, and if their mass is 190 pounds, then their weight is also 190 pounds. So the numerical value is the same. In contrast, if we're talking in the metric system, and our emphasis will be pretty much equal between the two systems, but in the metric system, if you want to find the weight, you take the mass m and you multiply by g, where g is the gravitational constant, or the gravitational field, if you want, for the Earth. That's the value g that I referred to last time as the acceleration due to gravity. So bottom line, if you want to go from kilograms to newtons on the Earth, you multiply by 9.81. 9.81, okay? And these are the units here, meters per second squared. But the key thing is you multiply by 9.81. And when you go from mass to weight for the imperial, they're equal. So there's no conversion required. So this is where I get irritated. This is where I get irritated. I'm watching the Olympics, and I love watching sports, especially the Olympics, and I like watching all kinds of stuff from, like, the track and field to the team sports to, for example, weightlifting or judo or whatever, okay? And it really bugs me when I hear people say, for example, in judo, they'll say the 60 kilogram weight class. You see how that really doesn't ring well in your head? 60 kilogram weight class. Because kilograms is not a weight. Kilograms is a mass. So that's just something annoying to somebody like me who's trained a lot in physics. But anyway, I've told you about other things, like when people confuse speed and velocity, especially when they're saying the weather, for example. Anyway, let's go over here and have a laugh at the next question. So, can someone let me know in the chat, what is the weight of a 253 pounds mass? What's the weight equal to? That's right, Jai. It's that simple, people. Now, I'm not going to tell you this is on your test or something, but I will tell you in the diploma program, I teach a similar topic, and on their final test every semester, I tell them, I'm going to give you a question this ridiculous, this easy. And then the test comes around, and the people that have come to class, like you, know the question, and as I walk around the room and say hi, they're like, thank you, sir, for that question. And on the other hand, you get a few people that weren't coming to class and they put their hand up and they say, I don't understand the question, sir. And I say like this, it's a gift, you're welcome. And I walk away. And I'm not trying to be mean, I'm being friendly. It's the easiest question ever. So anyway, let's go to the next one here. And do you know the difference between tons and tons? I know that sounds funny for me to say that, but it's not written here anywhere. So let me just differentiate the two here, okay? So 1 ton is equal to 2,000 pounds. I think you should know that. I think you should know that from your past experience. But if you don't know that, now you know it. 1 ton is 2,000 pounds. Since it's an imperial quantity, the answer is simply that. We can just say that the weight is equal to is equal to 1 ton. The weight is equal to 2,000 pounds. They're both right. Both answers are correct, by the way. Both answers here are spot on because it's in the imperial system, okay? When it's imperial, mass and weight, the numerical value, the number is the same, as long as you're sticking to imperial units. So those two questions are not meant to confuse you, they're meant for you to clarify the difference. So let's go to 27 now. A few more of these, I think, and then we'll be doing application questions. So in this case, though, we're in the metric system. Times 9.81. And can someone give me a number on that? Yep. I'm going to go to 3 sig figs, Jai. I appreciate that. And there you go. So in the metric system, remember that kilograms needs to be multiplied by meters per second squared to get newtons. In fact, going back to Joshua's comment earlier, if you recall, I mentioned that we need newtons, kilograms, and meters per second squared together. They are a package deal. So in this case, yes, there are two types of tons. And it's Ravi, it's hilarious that you just said that because that's the next question. And there it is. Do you see the spelling on this one's different? It's this. Awesome. So this first question was TON, which is imperial tons. 1 ton is 2,000 pounds, whereas that's TONNE, and 1 TONNE, or a metric ton, is 1,000 kilograms. Also a very good question is what's bigger? What's bigger, everybody? Let me know. Is this bigger or is this bigger? Which one's bigger? The first one or the second one? Yeah, that's correct, Ravi. Very good. That's very good. Yeah, because for those that don't know, 1 kilogram is equal to 2.2 pounds. So 1 ton, whoops, that's lots of N's. That's equal to 2,200. It's actually 2,205. I want to be a hero, but I'll put the 05 there. It's about 200 pounds more. So the difference between a metric ton and an imperial ton is the metric ton is 200 or so pounds greater. So going back to this question, if we want to find the force of gravity, I'm going to recycle this. I'm just going to recycle this comment here. Yeah, no. TON, it's right here, Joshua. TONNE is metric. It's right there, okay? Yeah, that's right. You got that. That's perfect. Sorry, I didn't mean to correct you. I was just clarifying for everybody else. Nothing to correct on your side. You're good. So we have 1,230 kilograms. I converted here from 1.23 metric tons into kilograms by multiplying by 1,000. So I'll just clarify that here. 1.23 tons is equal to 1,230 kilograms. So does someone have a number here for the answer? The 3 significant digits, please. Very good. Thank you very much. All right, my friends, I think that's enough for tons and tons and tons. So hopefully it wasn't too dangerous. But I think we can go and just manipulate a couple of metric calculations, and then we can continue on our way with some vectors review. So everything that we do after 2 more examples is really more just test review for you for next week. In this case, we want the mass in kilograms of a 500 Newton weight. So remember, the formula is weight equals mg, and that's in the metric system. In this case, the mass is equal to weight divided by g, which is 500 newtons divided by 9.81 meters per second squared. And if someone would be so kind as to do that calculation, please. Very nice, thank you. And I can recycle that for the next question as well. Recycle the same work here. Now, keep in mind that it's 3.52 kilonewtons. What does kilonewtons mean? Can someone clarify for the class what are kilonewtons? Yeah, 1,000 newtons. So this is 3520. Now the reason I'm showing you these questions is twofold. I need you to really understand the difference between mass and weight in both systems, but I also want you to be aware of kilonewtons and the conversion to units of newtons, because we need those when we start doing some some statics calculations in the final weeks of the course. In this case, I'll just put the answer. It's around 360 or so. Is that correct? Someone correct me. Is it 360 or somewhere there? 359. That's pretty good. Not bad. Not bad. Especially for 8:30 in the morning. Usually my brain doesn't start working until 10. But anyway, I'm sure that a lot of people here we're kind of probably split as a class between morning people and not morning people. But anyway, that's another statistical concept. So, everybody, I hope that you were good with that introduction. I really just wanted to show you some ideas about Newton's second law, especially. Also, we found the distinction between mass and weight in both systems. At this point, we're going to do vector application questions, and I'm just going to look ahead toward the end, 31 to 40. There's 10 questions here. I know that we have about an hour and a half, less a break, of course, before we do the quiz. So I'm not going to do the questions in order, if that's okay. I'm just going to scramble them around a little bit, and I might skip a question and come back to it. I might say, oh, try this one for homework or whatever, and just be a little bit on your toes with that, because I'm not trying to mess up your day or anything. There's a lot of redundancy in these questions, so it'd be nice for you to try these on your own as well. But anyway, we can do 31 together as a group. So an object is being pulled to the right by a force of 250 newtons. It's inclined at 35 with respect to the horizontal. And this question simply wants the components of the force. So I hope that you really see that what you're getting in this question is a review of components. Here's the force, 250. And that's 35 degrees. So this question is simply asking you for the two components, which I'm just going to call fx. How cool is that? Little arrows here and there, little prettiness, little pizzazz, little spicy. Okay. Okay, in this question, it's a little bit of a variation of the previous one. In this case, the 310 Newton force is inclined, but it's 40 degrees with respect to the vertical. No, you don't have to put arrows on the test, Joshua. Don't worry. It's very hard to type arrow stuff and whatever. I'm just having some fun with you here. Let's put right here. I feel bad now. In this case, we have a 310 Newton force, and we have the components with respect to the vertical direction this time. And this is 40 degrees. So 100%, this question might cause some problems for people if they don't know their trigonometry well. Because in this case, the x and y components, the cos and the sine are reversed. Because if you look at SOHCAHTOA, opposite, adjacent, etc., this time the cosine refers to the y direction and the sine refers to the x direction. I'm not using the cast rule here. I'm not using the fancy stuff that we did before. I'm just using very basic triangles. So can someone please do those calculations? 310 sine 30, sine 40, my bad. I hadn't corrected the angle. So 310 sine 40 and 310 cos 40. I got 199 for the first one. Can someone give us the second one? Thank you, Brian. And the second one there, the y value, the y component. Very good. So let's say that you're writing a test and you're like, did I get the right answer? Like, how can I do a quick check? So here's a cheap little check, okay? Cheap check. I know that if I do the Pythagorean theorem, I should get approximately, I should approximately get 310. I'm not going to check it right now on my calculator for the sake of time, but you should get that 310 here because this is a right angled triangle, and these are the legs of the triangle, which should form the hypotenuse length through the Pythagorean theorem. Okay. The next question comes straight out of a physics textbook, but it's also from your textbook as well. It's a very classic question involving ramps. It's a question that I'm not so inclined to put on a test, but since it's in the notes, I am going to go through it. So we have a car that's held on a ramp by two forces. I'm not saying this won't be a test question. I'm just saying that it's not going to have this many words, and it probably will. You'll be given a picture, if at least for a test. So there are two forces. There's one force of the brakes, and then there is the ramp that's pushing up on the car. And the question is to find what the force of gravity is. So for those that have studied physics here, they have a little bit of an advantage in terms of drawing the diagram. But once you have the diagram down, then it's really not, it doesn't matter if you've taken physics or not. It's just a picture. And here's the car. Now I'm going to just draw a block, but that's a car. There are three forces acting on this car. There is the force of the brakes. Now the brakes are going to go this way because the car is going to want to fall down the ramp. It's going to want to slide down the ramp. So that's the brakes. B for brakes. There's also a force of the ramp pushing up on the car. So that's this force here. See, the ramp is pushing on the car. I'm going to draw the force over here. It's not a pull, but I'm going to draw it as if it's being pulled. And I'm going to call that FR for ramp. So we have the brakes and the ramp. That's what these subscripts refer to. There's one additional force, which is gravity, which is this way. You can call the force of gravity, or you can call it W. Remember we called it W before for weight? So I'll refer to it as W. In terms of some angles here, this is an angle theta, and we're actually asked to find the angle right here. It says what is the angle and what is the weight. So that angle there is the same as this angle here, using some very fun similar triangles. You can get all of these together and you can draw a right angle triangle because in equilibrium the forces have to add up to 0. So I'll start by drawing the weight, and then I will put the brakes here. And then come back up, and that would be the ramp force, and that's theta. And we know the brake force is 480. So you can use your basic trigonometry to get the weight and to get the angle. Again, I emphasize that this diagram here is pretty grotesque for people that are new to this type of stuff. And by no means would I want to give you a question on a test where you have to pull that diagram out of thin air. I promise you that when it comes to test questions, I'll try to find ones that have diagrams, at least for this kind of stuff. So if you have this picture, you're able to manage it a little bit better. For the sake of time though, I know that you can do Pythagorean theorems and SOHCAHTOA or whatever you want to use to solve this question, because all you need is SOHCAHTOA and Pythagorean theorem there. I'm just going to state the two answers, and you can check these later on your own. So there's the weight, and there's the angle of the ramp. Two significant digits of accuracy. So it's 8:42. I'd like to do some questions now that involve adding vectors with components. Just the skills that we practiced prior to the Newton's law that we started today's class with. So hopefully we can get a couple more questions out before we take a break, and then I will promise you a nice break. So here we go. In lifting a heavy piece of equipment from the mud, a crane exerts a vertical force, and then it also exerts another force from a cable from a truck, and those forces together are going to be applied to this piece of equipment. So the question is saying, find the resultant of these forces that are acting on the object. Now, gravity is also acting on this object, but we're not asked to find gravity, and we're not asked to consider gravity in this question. It's just saying, find the resultant of those two forces. So what would benefit you most here is drawing something. Again, this type of drawing, though, I think you could just do it yourself. There's the first force, and here's the second force. In this case, there's no easts and wests, but there is left, right, up, and down. So can someone help me with the standard angles? What is the angle between, remember, the standard angle is 0 to 360. Can someone tell me what angle this would be between 0 and 360, this vertical one here? Thank you, everybody. That's right. That's a 90-degree angle. And then this angle would be what between 0 and 360? Yeah, it's 10. It's just the easy number 10. I want to make a note here before we finish the question. Nice quick note here. I'm just going to say that at the bottom of the page. If you want to use sine cosine law, be my guest. I told you from the beginning of this unit, though, that I would be using components as much as possible, even for questions where you probably don't need it. So I'm going to just whip up the solution here. This might be too much for you to copy in a short time, but I'm just going to walk you through the solution. So my advice to you is don't try to scramble writing this down. My intention is not that you can write this down in 5 seconds. I just want you to see that the setup is almost there for you, though. So there's the 90 and the 10 that you talked about. See, 90 and 10. The magnitudes are 6,500 and 8,300. So really the centerpiece of this question is the table. So here's the actual table. And if you look at the x and y components, we do here, how do we get these numbers into these numbers? Remember, the formula is always, when standard angles are used, we use sine and cosine. So I'll just remind you here with a quick jotting of the notes. Remember that f I x equals f I cos theta I, and f I y is sine theta I. So that's where I'm getting those components from. The x component is always the magnitude cos, and then the y component is the magnitude sine. Notice that we have a 0 here for the x component, which is clearly represented in this diagram. There is no horizontal component to the first vector. In fact, this first row of the table, all you really need is the 0 and the 6,500. Now, when it comes to your test, this stuff here, I just want to be very clear with everybody. When it comes to a test, this is all the stuff that I care about. This blue stuff here. When you look at the first half of this question, everything that I wrote like this, see that? Anything here, I don't care about this. If you wrote this, if you get these numbers in blue correct, if you get those numbers in blue correct, I'm good, and you're good too. So if you're wondering how much do I need to write on a test, because there may be a question on your test, there certainly is a question on your assignment today like this, where I ask you to actually write some stuff down. I want to see this on your assignment today. I want to see something like this, and there will be room provided for you to do that. So when we get close to the assignment, I will bring that up in the discussion, because your assignment is a little bit special today. I've added a question in there that's not very it's not a one answer. It's like you have to show your work. You can write a little bit in the box, a lot more than usual. Anyway, so that's basically the component sums. Upon looking at your assignments in the past, I've noticed that you've been doing well with these. Some small errors here and there, but generally speaking, I see some good work. Now we're going to reconstruct the final answer. So we have a positive number here and a positive number there. So that means it's to the right and it's up. So this is 8174 and this is 7941. So now you need to find the angle theta and you need to find f, which thankfully are right here. So that's what I'm solving for there. And you can see that the answer is presented in a notation that makes sense to the question. In other words, in this question, there's no east and west. We have to the right and we have up. So in this case, I've written it in sort of a sentence fragment. I have to the right at 44.2 degrees above the horizon. You could also write, I think you could write right 44.2 degrees up. If I can squeeze in this stylus here, I'd be happy with that. If you wrote that down, I completely understand the notation. Okay. So if you want to write something like that, be my guest. I know that some physics teachers would cringe at that notation, but I'm cool with it because you're learning a very large amount of information in a very short time. So there's a couple more questions here that I think would be fun for you to do for homework. I'm going to post these on Blackboard, and I'm just going to put here homework. I'll put homework and then I'll put time permitting because I don't know if we'll have time to do both of these. The first question comes right from the textbook, and the second one as well comes from the textbook. I think I might have changed the numbers, but it's this second one, 36, is probably not for a test because it's not a construction question. What was that for the previous question? 11,400. You're welcome. Sorry. I think it's a good idea to maybe take a break at this point. Let's take a break until 9 o'clock, okay, everybody? Give you time to copy this question down if you need to copy something. I'll be back at 9 o'clock, okay? So in this example, we're going to continue with some practice of vector addition. Here we're adding together for the resultant for 4 forces, and it's oriented in the northeast-southwest plane. We're looking for the resultant of these forces, and that means we want the vector sum. So what would most be appropriate is that you give an angle for each of these vectors between 0 and 360. This is a question where you don't want to use sine and cosine law because it could definitely take you a while to go 2 triangles at a time. So as I go around the loop here, I'd like you to tell me what the angle is between 0 and 360 for each of these vectors. So for this first vector, what would be the angle for 6,500 pounds of force in standard position? So that would be 51 degrees. What about this one over here, the 3,900 pounds? What would be the angle in standard position for that force? That's correct, Jai. 122 degrees. Because we're measuring the angle from east. Remember, east is 0 degrees. This is 0 degrees. And we're trying to go all the way over here. Now this 5,100 pound force is going to be at an angle of what? What does this angle equal? 209 is correct, John. Thank you. And finally, this 2,300 pound force is oriented southward, so this angle is 270. Whoops. So there you have it. All four forces with all of their standard, their angles represented in standard position. So really this is where the method of components shines the most. So at this point you would, in my opinion, construct or organize a table where you have all of the forces and the respective components. So in this case, we have the four forces, which are 6,500 pounds, 51 degrees, that's the first one, and then 3,900 pounds at 122 degrees, there it is, and then 5,100 pounds at 209, and 2,300 pounds at 270. So there you go, all the way down the list there. We have the four forces with their respective angles and standard position. We can then find the components using the formula earlier, which was for the x direction, f cos theta, and for the y direction, f sine theta. So although I don't present those calculations here, hopefully you can find doing them nothing too dangerous over there. So there's all the components. So these are really the numbers that are critical to moving on in the question. But in any case, if we continue further down now, we can find the vector sums, which are, in this case, we get a negative answer in the x direction and a positive answer in the y direction. Whoops. So we can use those totals, and I don't expect you to do this in a very short time. Like this type of question, I would expect you to be able to do it in hopefully 8 to 10 minutes. It's not too much writing. It's really just getting the angles right. So once you have those vector sums put together, you can draw a triangle. In this case, we're going west and we're going north. So this is 2436. And this is 3586. So we can put that together and draw a vector sum as so. So there you go. At this point, all you really need is this angle. And this magnitude, which can be found using the inverse tangent and Pythagorean theorem. So to finish the question, I'm just going to refer to my solutions as well. And that completes the question. So we have our net force, or resultant force, I should say. And then we have an angle of 55.8 degrees, which when looking at the diagram indicates that it's north of west. So that's why we have here north of west. So if this type of question, if you're feeling good about it, then I think that you're in a fantastic position regarding the upcoming quiz and also the upcoming test, because you know you're going to get something like this involving more than two vectors. I've been using it in the previous booklet, and I've used it in this booklet now a couple times at least. What I'd like to do with you now in the remaining time is 3 more exercises. I think it's not too much of an ambitious undertaking, but the next one's going to involve a little bit of algebra, and hopefully it'll be. The test is next week, Ayo. The test is next week. Next Wednesday. Does anybody need more time on this question? You're welcome. Yeah. All right. I'm just going to step away. Sorry. The test is on chapters on units 10 and 11, but it includes this week's stuff. Yeah. Well, this week's stuff is mostly a review. I'm just going to show you the next question. Okay, so hopefully you've had time to read the question and we can take a look at it. So we have two ropes that are raising a crate, and the first force is aligned one way, whereas the second one is aligned a different way with respect to the vertical. And it says here, what must be the magnitude of the second force so that the crate is lifted upward? And I mean straight upward. So it has to go in a completely vertical direction and not go sideways. And then it asks for what is the maximum weight that the crate can withstand, that these ropes can withstand. So anyway, how do you approach this question? Well, maybe a diagram would be in order here. So we have the vertical direction here. Here's the crate. I'm just going to put a dot for the crate, a point mass. And then this is 240. And it's 25 degrees. And there's also another force that we don't know what the magnitude of it is. I'm just going to call it F2. And we're going to give it a direction of 35 degrees. And then we have the weight of the crate acting down, which is W. So this question, you can solve it using components. You can solve it using sine, cosine, tan, or sine law and cosine law. Well, there's lots of options here. So I'm going to show you a solution using components. But you can definitely use the sine and cosine law if you prefer. If we go with the component method, then we can talk about the angles in standard position. This force of 240 pounds is going to be at 115 degrees. And this force here is going to be at 55 degrees. The weight is going to be also of interest. And we can see that the weight is going to equal, well, it's going to have an angle of 270 degrees. So we can solve this question by looking at the x and y components of each of the vectors and computing a sum. So in this case, we can draw a table. So let me make a table here. So we can find the x and y components of each of those. Sometimes we'll require a formula, but let's see what happens here anyway. In this case, this is going to become the following. This is negative 101.428. Now, W cos 270. What's W cos 270? Well, it's 0. And then this is W sine 270, which is negative W. One more thing. The total here is 0, and the total here is 0. The reason that it's 0 is we're in equilibrium. When you're in equilibrium, the total has to be 0. Whenever things are in equilibrium in a system, the components must add up to 0. And now we end up with a system of equations that we can solve for F2 and for W. So at this point, it becomes an algebra question. Again, you don't have to do it this way. You can use sine and cosine law if you prefer. So the x direction, so if you do the x direction equilibrium, and then later you do the y direction equilibrium, you get the following. In the x direction, you get negative 101.428 plus F2 cos 55 equals 0, which tells you that F2 equals 177 pounds. And in the y direction, you can do that as well. So you can say that 217.513 plus F2 sine 55 minus W is 0. But you know that F2 is equal to 177 now. And then you can solve for W. I'll leave that for you for homework as an exercise. You should get 362 pounds. And that is pretty much that's pretty much how it goes. This may not be the most efficient answer, but it definitely is an answer for you to go through and to practice a bit more of your algebra skills. But it does warrant the discussion. What do you like better? Do you like the component method, or would you rather see this answered with sine and cosine law? So that's a question that I leave up to you. What do you like better? And if you're not sure about which way you like to do it, the good news is the next question, and really the last question we're going to do, is going to be both ways. So we're going to do question 39 and then question 40, which is the exact same question, but one way we're going to solve it with sine and cosine law, and the other way we're going to solve it using the method of components. And then you can make a decision about which method you prefer. Does anybody need more time with this question before we move on?
Yeah, Dr. J, sorry, I'm still trying to figure out for the x direction equilibrium, I'm still trying to figure out how to go from F2 cos 55 equals 101, how to actually figure out that it's 177. I'm just missing that part of it.
So turn cos 55 into a decimal, if you don't mind. I don't have that decimal in front of me. What's cos 55 as a decimal? Anybody?
It's roughly 0.57, but that makes it clear. I get how to go from there. Thank you.
You're welcome. 0.57-ish. Anyway, that's fine. Okay, and the same thing over here, you just do convert that to a decimal. Anybody want to tell me what cos 55 and sine 55 are to 4 significant digits in the chat, please? Any volunteers? Thank you. And sine? Thank you very much. All right, I think someone's mic's on. Sorry. I was just getting a little bit of feedback. Okay. That's okay. Not concerned. So let's move on to another question now, where we're going to treat the problem two different ways. So in this question, we'll use the sine law. And this question actually is the same question that we saw in the fall when we were talking about trigonometry. So we're going to try to solve for the tension T1 and the tension T2 for this system, which is in equilibrium. And I want you to just compare this solution to what we'll do after, where we use algebra. I'm not saying one's better than the other. I'm just saying that some of you may prefer to not use the sine or cosine law and just stick to components. So because this question's in equilibrium, we can draw what's called a forced triangle. Since we have seen this question in the past, I am going to go straight to the forced triangle, which is right here. So let's take a look at that and do a little bit of clarification here. There are three forces acting on the object. There's T2 going this way and T1 going this way, and then there's gravity going down. And because we're in equilibrium, I mentioned that you can draw the forces as a closed loop. See how it's a closed loop? We saw this behavior in an earlier question when we did the car on the ramp. If you remember the question with the car on the ramp, here's the car on the ramp. See? I drew a closed loop. The three forces acting on this car were in equilibrium, so you can draw them as a closed loop. So in this case, we have to do the same. And let's take a look at some of the angles here. There's a little bit of Z law action happening. See the Z law there? There's a Z there. Let me draw it better. There's a Z in green, and that's this Z right here. It's hard to keep my hand steady on this screen here, but there's the Z there. There's also a Z here, facing backwards. So this angle equals this angle, and then this angle equals this angle. So that's how I'm getting this angle here is 42, and this angle here is 30. So that's how I get the 42 and the 30 here. If you add those together, you get 72. And then at this point, you have a triangle for which you can use the sine law. So I'll just finish off by just doing that. I'm going to write the sine law, and I'm going to write the final answers. If you're wondering which method do I prefer, this method or the method to come, honestly, this method is way faster. But what I'm trying to say is that let's say that you exclusively want to use components. I said to you that you could solve all questions with components if you don't want to use sine or cosine law. So let me show you how you would answer this question using the method of components and what the trade-off is in terms of how much work you have to do. So let me give you a few minutes to copy that down, and then we'll resume class. So just a few minutes on your own to copy that down. So I'll be back in a few minutes to resume. Okay, back in business. So let's continue now with the final example. And this one's going to be a little bit more scary, but hopefully nothing too dangerous. Just a little bit of work, that's all. So in this case, we have the same question, but we're trying to consider what are the components instead of using the sine and cosine law. So let's take a look here. We have the same diagram, the same quantities, but just a little bit more fun here as we consider the components. So I'm going to just start drawing some of the angles and using standard position this time. So this angle is 30 degrees in standard position. This angle here is 90 plus 42, which is 132 degrees. And then you have this angle down here, which we already know is 270. So let's see how we would set this up using the method of components. I'll construct a table as we did for the previous question, and then we'll proceed from there. So there's three forces acting. The first force will be, I'll call it T1. I'm just doing them in the order of the forces. So there's T1 with an angle of 132 degrees. There's T2 with an angle of 30 degrees. There's 175 pounds with an angle of 270 degrees. And that total for this situation is going to be 0 because we are in equilibrium. What do we have in the directions in the x and y here? We have T1 cos 132, T1 sine 132, T2 cos 30, and T2 sine 30. And then for the last one, we have 0 and negative 175. And hopefully you can see how the setup here is very similar to what you saw in the earlier example where we were lifting a crate. This question is in equilibrium. That's why the totals are 0. We don't actually care about solving for a total. We care about setting up a system of equations from which we can solve for T1 and T2. I think we have everything in order here that we can do that. So if you look at each of the equations, we can set up a system. So there's the system of equations. So let's walk you through that here. In the first column, we have T1 cos, I think that's supposed to be 138. Is that a typo? Sorry, I think there's a typo here. This is supposed to be 138. I apologize. Did someone else see that it's 138 as well? Anybody else see 138 there? Yeah, but the 42 is wrong, Ravi. That's my bad. See this 42 here, this is 42 here, which is this is 42. That angle there's 42. So this angle here is 180 minus 42. That's my apologies there. I just realized that mistake now. It's because of the Z law. There's a Z law there. So it's a little tricky one. At this point, I think that we're in a position where we can solve for T1 and T2 if we can just get past all these trig ratios. So my advice to you here is to just take your calculator and type in all those trig ratios, and you'll end up with this system here, which is a little bit cleaner. And from that point, I think we're good. I think at this point it turns into a linear systems question, the likes of which you haven't seen for a few months, but regardless, you should be able to solve for using a method of your choice. You could use substitution, elimination. If it was an assignment, you could use graphing. You could graph these. I'm going to assume that we're writing a test or a quiz, so I'm going to use the method of substitution. So what I did was I solved for T2 in the first equation. So here's that step. I took the first equation here and I just moved this term to the other side and divided by 0.8660 and ended up with an equation here of T2 in terms of T1. So T2 is equal to this. So once we have that out of the way, then we can consider substituting that back into the second equation. So what you can do is take this here and plug it in right there, which is what I did on the next step. And from there, the question really just falls apart and things are good. So I'm just going to put down the rest of my answer here. So there's the rest of the question. And you can see here that after you substitute in the term here, you can multiply by a half, collect the like terms, and divide 175 by this number 1.0981 to get your final answer of 159 pounds. This is the same answer that we had in the previous example, so we do get the same answer. And to complete the question, you can plug in 137. You can get the answer of 137 pounds by plugging in the 159 pounds back into the T2 equation here. So if you take 159 and multiply by 0.8581, you'll get the 137 pound force. Okay, so that's pretty much it. That's pretty much it, okay? Are there any questions or concerns about that? Okay. I'd like to talk to you a little bit about your quiz now.